astronauts come back from space, but something is wrong, not with their muscles, not with their bones, with their brains. The structure inside their skull actually shifts. Parts of it move, fluids build up where they should not. And some of these changes do not fully return to normal, even after months on Earth. The most disturbing part is this. Space might not just affect the brain, it might permanently rewire it. Space looks calm, silent, almost peaceful, a place where everything floats, a place free from the weight and pressure of Earth. But that calm is deceptive because the human brain was never designed for this environment. For millions of years, it evolved under one constant force, gravity. Every movement, every signal, every sense of direction depends on it. The brain uses gravity as a reference point for reality itself. Remove that force, and the brain starts to lose its anchor. In zero gravity, there is no up, there is no down, there is no natural orientation. The signals that the brain has trusted for a lifetime suddenly stop making sense. The inner ear, which normally detects motion and balance, becomes unreliable. The body sends confusing information. The eyes see one thing, the inner ear says something else. The brain is forced into a situation it has never experienced before in human history, and it has to adapt. At first, the effects seem simple. Astronauts feel disoriented, they feel dizzy. Many experience space motion sickness in the first few days. But that is only the beginning. What scientists discovered later is far more serious. The brain does not just struggle, it changes. Inside the skull, fluids begin to shift. On Earth, gravity pulls fluids downward. Blood, water, and other fluids are constantly being redistributed by this force. In space, that force disappears. Fluids move upward toward the head. This creates pressure inside the skull. The face becomes slightly swollen. But the real impact is hidden deeper. The brain is surrounded by a protective liquid called cerebrospinal fluid. This fluid cushions it and keeps it stable. In zero gravity, this fluid does not circulate in the same way. It begins to collect in certain areas. Pressure builds, and the brain, no longer held in place by gravity, starts to float slightly upward. This is not a theory. It has been measured. Advanced brain scans taken before and after space missions show clear changes. The position of the brain shifts. The shape of certain regions changes. Areas linked to movement and coordination are affected the most. It is a slow, silent transformation, one that astronauts cannot feel directly as it happens, and it does not stop there. The brain is not a fixed organ. It is constantly adapting. This ability is called neuroplasticity. It allows the brain to rewire itself based on experience. In space, this process accelerates. The brain begins to reprogram how it understands movement, balance, and even orientation. Since the inner ear is no longer reliable, the brain starts depending more on visual information. It learns to trust what it sees rather than what it feels. Over time, this becomes the new normal. The brain builds a completely different system to function in zero gravity. This adaptation helps astronauts survive in space. But it comes at a cost, because when they return to Earth, gravity comes back. Suddenly, the old rules apply again. The inner ear starts sending signals that the brain has learned to ignore. The body feels heavy. Movements feel wrong. Walking becomes difficult. Standing upright feels unstable. It is like learning to live in a completely new body. Some astronauts describe the experience as deeply unsettling. Simple tasks become challenging. Balance is off, coordination is weak. The brain needs time to readjust. In some cases, it takes weeks. In others, months. And here is the part that raises serious concern among scientists. Not all changes fully reverse. Studies have shown that even after long recovery periods, certain structural differences in the brain remain. The fluid distribution does not always return to its original state. Some neural pathways stay altered. The brain that returns is not always identical to the one that left. This is a problem that becomes much more serious when considering long missions. Trips to Mars, for example, could last years. That means prolonged exposure to zero gravity, longer time for the brain to adapt, and potentially more permanent changes. Scientists are still trying to understand the full impact. How far can the brain adapt before the changes become irreversible? Can the brain fully recover after extended missions? Or will future astronauts return with lasting alterations that cannot be undone? These questions are not just theoretical. They are critical for the future of human space exploration. Because sending humans deeper into space is no longer just a dream. It is a plan. Missions are being designed. Timelines are being discussed. But the human brain remains one of the biggest unknown risks. This video will take you deep into what actually happens inside the human brain in zero gravity. Not just the surface effects, the real changes, the hidden shifts, the disturbing discoveries that most people never hear about. You will learn how the brain physically moves inside the skull, how fluid buildup creates pressure that affects vision, how the brain rewires itself to survive in space, and why returning to Earth can feel like entering a completely different world. By the end, you will see space in a very different way, not just as a place of beauty and exploration, but as an environment that challenges the very core of what makes us human. Welcome to the channel. If you want to explore the darkest and most fascinating truths about space, science, and the universe, make sure to subscribe. The moment gravity disappears, the body loses one of its most constant forces. On Earth, every drop of fluid inside the body is pulled downward. Blood flows with that pull. Pressure distributes in a predictable way. The brain sits in a stable position, held in place not just by tissue, but by gravity itself. In space, that system breaks. Fluids begin to move upward. Blood shifts toward the head. Water inside the body follows the same path. Astronauts often notice it within hours. Their faces look fuller. Their heads feel heavy. It is not just a surface change. Inside the skull, pressure starts to build. The skull is a closed space. There is no room for expansion. When extra fluid moves in, something has to adjust. That pressure pushes against the brain. Slowly, subtly, the brain begins to change position. It does not fall or collapse. It drifts. Without gravity pulling it downward, the brain is no longer anchored in the same way. It shifts slightly upward inside the skull. This movement is small, measured in millimeters. But in a system as delicate as the brain, even a tiny shift matters. Scientists did not expect this at first. The idea that the brain could physically move inside the skull sounded extreme. But advanced imaging told a different story. MR1 scans taken before and after space missions revealed clear changes. The brain had moved, not dramatically, but enough to be measurable and consistent across astronauts. Certain regions are affected more than others. Areas near the top of the brain show compression. The spaces that normally contain fluid begin to shrink in some places and expand in others. The entire internal balance shifts. This movement has consequences. The brain is not just an organ, it is a network of highly organized structures, each responsible for specific functions. Movement, coordination, balance, spatial awareness. These systems depend on precise positioning and communication. When the structure shifts even slightly, the signals can change. Regions that help control movement begin to behave differently. Coordination becomes less stable. Actions that once felt automatic require more focus. The brain is forced to adjust to a new internal layout while also dealing with a completely unfamiliar environment. There is another layer to this that makes it more disturbing. The shift is not uniform. It does not happen in the exact same way for every astronaut. Some experience more pronounced changes, others less. The reasons are still not fully understood. Factors like mission length, individual biology, and even genetics may play a role. This unpredictability makes it harder to control. The longer a person stays in zero gravity, the more time these changes have to develop. The brain continues to adapt. it continues to shift, and the body continues to operate under conditions it was never designed to handle. At the same time, the pressure inside the skull does not simply stabilize and stop. It interacts with other systems. It affects how fluids circulate around the brain. It begins to influence areas connected to vision, perception, and spatial awareness. The brain is not just moving. It is entering a completely new physical state. Inside the skull, the brain is surrounded by a clear liquid that most people never think about. This liquid is called cerebrospinal fluid. It acts like a cushion. It protects the brain from sudden movement. It also helps remove waste and keeps pressure stable. On Earth, this fluid is constantly moving. It flows in a slow, controlled cycle. Gravity plays a quiet but important role in that process. In space, that balance is disrupted. Without gravity, the normal flow of cerebrospinal fluid begins to change. It does not drain the same way. It does not circulate with the same rhythm. Instead, it starts to gather in places where it should not stay for long. The movement becomes uneven. Some areas experience a buildup, while others lose the balance they depend on. This buildup creates pressure. The skull cannot expand to release that pressure. There is no space for extra fluid to go. As cerebrospinal fluid accumulates, it pushes against the brain from the inside. It presses on delicate structures. It alters the environment the brain relies on to function properly. Astronauts cannot feel this directly at first. There is no sharp pain, no sudden warning. The process is slow and silent, but over time the effects begin to appear. One of the most serious outcomes is a condition known as spaceflight-associated neuroocular syndrome. Scientists shorten it to SANS. It is one of the most concerning discoveries in long-duration space missions. This condition affects the eyes, but the origin is inside the brain. As pressure builds from the excess fluid, it begins to impact the optic nerve. This nerve connects the eyes to the brain. It carries visual information that allows a person to see clearly. When pressure pushes against it, the signals can become distorted. Astronauts start to notice changes in their vision. Some report blurred sight. Others struggle to focus on objects that were once clear. Straight lines may appear slightly curved. In some cases, the shape of the eye itself changes due to the pressure from behind. These are not minor issues. They can persist even after returning to Earth. Medical scans have shown that the back of the eye can flatten under this pressure. The optic nerve can swell. These changes are not always fully reversible. For missions that last months, the risk increases. For missions that could last years, the consequences are still unknown. There is another detail that makes this more unsettling. The body has no quick way to fix it. On Earth, gravity helps regulate fluid distribution naturally. In space, that system is gone. Scientists have tested different methods to reduce the buildup. Special suits that apply pressure to the lower body. Devices that create artificial gravity for short periods. None of them fully solve the problem. The brain and eyes remain under constant stress. As the fluid continues to accumulate, it adds another layer of pressure to an already shifting brain. The delicate balance inside the skull becomes harder to maintain. Structures that depend on stability begin to operate under strain. And this pressure does not just affect vision. It starts to interfere with how the brain processes movement, balance, and spatial awareness. The human brain is built to adapt. It changes constantly. Every new skill, every new environment leaves a mark. This ability is called neuroplasticity. It allows the brain to rewire itself, to form new connections, to replace old patterns with new ones. On Earth, this process is gradual. It follows the rules set by gravity, by balance, by a stable sense of direction. In space, those rules collapse. The brain is forced into a situation where its most trusted systems stop working the way they should. The inner ear, also known as the vestibular system, is one of the first to fail. On Earth, it detects motion and orientation. Tiny structures filled with fluid respond to gravity and movement. They tell the brain which way is up, which way is down, and how the body is positioned in space. In zero gravity, those signals lose meaning. The fluid inside the inner ear no longer settles in a consistent direction. It floats, just like everything else. The sensors that once gave clear information now send confusing signals. The brain receives data that does not match reality. Movement feels wrong. Orientation becomes uncertain. The system that once worked perfectly becomes unreliable. At first, the brain struggles to cope. This is why many astronauts feel disoriented in the early days of a mission. Their senses are in conflict. The eyes say one thing. The inner ear says something else. The body feels disconnected from its surroundings. Simple movements can feel unnatural and unstable. But the brain does not stay confused for long. It begins to adapt. Since the signals from the inner ear can no longer be trusted, the brain starts to shift its dependence. It looks for another source of reliable information. It finds it in vision. The eyes become the primary guide for movement and orientation. The brain starts to rely more heavily on what it sees rather than what it feels. This change is not temporary. It is structural. Neural pathways begin to reorganize. Connections that once prioritized balanced signals weaken. New pathways strengthen around visual input. The brain rewires itself to function in a world without gravity. Movements become smoother again. Coordination improves. The astronaut starts to feel stable in an environment that once felt chaotic. This adaptation is powerful. It allows humans to survive in space, but it also creates a new problem. The longer the brain stays in this state, the deeper the changes become. Over time, the new wiring becomes more established. The brain becomes efficient in zero gravity. It builds a system that works for that environment. But this system is not designed for Earth. It is built for a place where gravity does not exist. There is evidence that these changes can affect how the brain processes motion even after returning home. Some astronauts show altered responses in balance tests months after their mission. Their brains continue to rely more on visual cues than before. The shift does not fully reverse. There is also a lesser-known effect. As the brain rewires itself, it can begin to reinterpret basic sensations. Movements that once felt automatic may require conscious effort. The sense of body position, known as proprioception, can become less precise. The brain has to rebuild its understanding of where the body is in space. This constant adaptation places the brain under continuous strain. It is learning, unlearning, and relearning at the same time. And while it becomes better suited for life in zero gravity, it moves further away from the conditions it was originally designed for. That growing gap begins to affect not just movement, but the very way reality is perceived. In space, direction stops making sense. There is no natural up. There is no true down. On Earth, gravity defines everything. It tells the body where it stands. It tells the brain how to organize the world. Walls, floors, ceilings all have meaning because gravity gives them meaning. Remove that force, and the brain loses its reference point. Astronauts enter an environment where every direction feels the same. They can float upside down without realizing it. They can turn slowly and lose track of orientation within seconds. The brain tries to assign structure, but nothing stays consistent. A surface that feels like a floor in one moment can feel like a wall in the next. This creates spatial disorientation. It is not just confusion. It is a deeper breakdown in how the brain understands space. The internal map that the brain uses to track position begins to fail. Signals from the body no longer align with what the eyes see. The brain receives information, but it cannot organize it into a stable picture. Movements become uncertain. A simple turn can feel exaggerated. A small push can send the body drifting farther than expected. The timing of motion changes. The brain predicts one outcome, but the body experiences another. This mismatch forces constant correction. Every action requires more attention. There is a lesser-known effect that makes this even more disturbing. Some astronauts report a sense of detachment from their own body. It is not a loss of control. It is a shift in perception. The brain struggles to link movement with sensation. Actions feel slightly delayed or disconnected. The body moves, but the experience of that movement feels distant. This sensation is subtle, but it can be unsettling. The brain depends on a system called proprioception to understand where the body is in space. It uses signals from muscles and joints to track position. In zero gravity, those signals change. Without weight pressing on the body, the feedback becomes weaker. The brain loses part of its awareness. This adds another layer to the confusion. Vision tries to take control, but vision alone is not enough. The brain is used to combining multiple signals to create a stable reality. When those signals conflict, the brain has to choose which ones to trust. In space, that choice is not always clear. Astronauts often create their own sense of orientation to cope. They may choose a direction to treat as down even though it has no physical meaning. This is a mental adjustment, not a physical one. It helps reduce confusion, but it does not restore the natural system the brain relies on. Over time, the brain attempts to rebuild a new map of reality. This map is different from anything experienced on Earth. It is flexible. It changes based on visual cues and movement patterns, but it lacks the stability that gravity once provided. The brain is constantly updating it, constantly correcting it. There is no fixed frame of reference. This constant recalibration increases mental load. Tasks that were once automatic now require focus. Orientation is not assumed. It is calculated. Every movement becomes part of an ongoing process of adjustment. And as this distorted sense of reality becomes normal, the brain begins to accept it as the new baseline. The return to Earth does not feel like coming home. It feels like entering a foreign world. Gravity comes back all at once. The body feels heavy. Every movement carries weight again. The brain, now adapted to a weightless environment, is suddenly forced to switch back. And it does not happen smoothly. Astronauts often struggle the moment they stand. Their legs feel unstable. Balance is weak. Simple actions like walking in a straight line become difficult. The brain sends signals, but the body does not respond the way it should. The system that once worked perfectly now feels out of sync. The inner ear begins sending strong signals again. It detects gravity. It senses direction. But the brain has spent weeks or months learning to ignore those signals. It no longer trusts them. This creates a conflict inside the brain. Old systems try to take control. New adaptations resist. The result is disorientation. Astronauts can feel dizzy. Some feel like the ground is moving under them. Others struggle to keep their posture stable. Standing still can be as challenging as walking. The brain has to relearn how to interpret basic signals that once required no thought. This process takes time. The brain begins to reverse its changes. Neural pathways that were weakened start to rebuild. Connections that relied heavily on visual input begin to adjust. The inner ear slowly regains its role as a primary source of balance. But this reversal is not instant. It is slow and uneven. There is a lesser-known detail that makes this phase more complex. Muscles and joints send stronger signals again because of gravity. The body feels pressure in ways it has not felt for a long time. The brain has to process this renewed input while also correcting its internal map of movement and space. Every step becomes a form of retraining. Some astronauts recover within weeks. Others take months to feel normal again. And in some cases, normal never fully returns. Studies using advanced brain imaging have shown that certain structural changes can remain long after the mission ends. Fluid distribution inside the brain may not fully return to its original state. Some regions continue to show differences in shape and position. The brain carries a physical record of its time and space. There are also subtle functional changes. Balance tests have revealed that some astronauts rely more on vision even after recovery. Their brains continue to favor the adaptations formed in zero gravity. This shift may not be noticeable in daily life, but it shows that the brain has not completely reset. The duration of the mission plays a critical role. The longer a person stays in space, the more deeply the brain adapts. These changes become stronger and more stable over time. When the brain has spent months or years operating under a different system, reversing that system becomes harder. The process is no longer just adjustment, it becomes reconstruction. This raises serious concerns for future missions. Extended journeys, such as those planned for Mars, would expose astronauts to zero gravity for far longer periods. The brain would have more time to change, more time to drift away from its original state. When those astronauts return, the challenge will not just be physical recovery. It will be restoring a brain that has learned to function in a completely different version of reality. Zero gravity does not just challenge the human body, it reaches deeper. It changes the brain itself. What begins as a survival response slowly becomes something more serious. The brain shifts inside the skull. Fluids build pressure in places that were never meant to hold it. Systems that once worked perfectly begin to fail, then rebuild in a completely different way. The brain rewires itself to survive in an environment it was never designed for. And the longer it stays there, the more those changes settle in. Some of them fade after returning to Earth, but not all. Certain effects remain. Subtle differences in structure, small changes in how the brain processes movement and balance, a new way of functioning that does not fully return to its original state. This is the part that scientists are still trying to understand. Humanity is preparing to go further into space than ever before.
Missions to Mars are no longer just ideas.
They are being planned in detail. These journeys will take months, even years. That means the brain will spend more time in zero gravity than any human has ever experienced. The question is no longer whether the brain can adapt. The question is how far that adaptation can go. At what point does change become permanent? At what point does the brain stop returning to what it once was? And if that limit is crossed, what does it mean for the future of human exploration? Space is not just testing machines. It is testing the human mind at its core. If this changed the way you see space, make sure to like the video. And subscribe to the channel for more deep and unsettling truths about science and the universe. Because the more we learn about space, the more it reveals something unexpected. The greatest risk may not be the distance. It may be what it does to us along the way.